7.3, using matrices to solve systems of linear equations. So this is basically just another way to solve the same sort of systems we were doing in the last section. A matrix is just a rectangular list of numbers. We use them a lot to organize data and solve our problems a little bit more efficiently so that we can just see it a little bit cleaner. The format is like you see here in the example, usually with square brackets. We have 2, 3, 1, 5, 7, 4. This is a 2 by 3 matrix, and what that means is that it has 2 rows and 3 columns. Your book specifies this through m by n for the dimensions of the matrix. It's just the number of rows times the number of columns. If we're trying to locate a specific number inside of a matrix, we give it an ordered pair, kind of like when we do graphing, but in this case there will just be numbers. There won't be any decimal values because it corresponds with the row and the column position of that number in the matrix. So if I asked you what is at position 2, 1, you would be looking at the second row and the first column, which is where we see a 5. If I said what's at position 2, 3, you'd look at the second row and the third column where you see a 4. And the first row, second column, you would say, okay, first row, second column, that's a 3. And so on. In order to solve these linear equations, what we will do is build something called an augmented matrix, because it'll have effectively the left-hand side of the equation and the right-hand side of the equation, and then we draw a line between the left and right side. So if I give you a system like 2x plus 3y equals 1 and 5x plus 7y equals negative 4, then the left side is the 2, 3, 5, 7, and the right side is the 1 and the negative 4. And then we just have this vertical line to separate the left side from the right side of these equations. We'll apply the same kind of elimination to get it into triangular form, but the triangular form that we're looking for corresponds with just the left side of the augmented matrix. The right side will change, as you can see, but we only really care about getting the triangular form on the left side. So to apply the elimination on this one, I want to get rid of the 5. So in order to make the 2 look like a 5, I have to multiply it by 5 halves, because if I divide 2 by 2, I get 1, and then if I multiply by 5, I get 5. So I subtract 5 halves of row 1 from row 2, and that gets 5 minus 5, 7 minus 15 halves, and negative 4 minus 5 halves. Notice, right, what I did is exactly the same as what we did in the last section. It's just now we just have numbers instead of dealing with x, y, and z. So that gets it into triangular form. 2, 3, 1 stays the same, but the second row changed to 0, negative 1 half, negative 13 halves. And so the operations that you can make that won't change the solution are if you add the rows algebraically like we just did, right? Some combination, but you want to keep row 2 just row 2. You never want to you don't want to multiply row 2 by something at the same time. You want to do that as a separate operation. You can multiply rows by a constant to make things simpler, like the second row here I would like to multiply by a negative 2 to make it 1. And we can also interchange rows without changing the solution. So if I just wanted to flip the rows, I can do that without changing the solution at all. Then once we've done those operations, what we're trying to do is get it into the simplest form possible to get a solution. So what we want to do here is try and turn the points that correspond with the variable that we care about, which was usually the first one in triangular form. So for the first equation, that would be the x, or the very first position. For the second row, that would be the second position, or our y. And when we have a 3 by 3, that third one would just correspond to the z. So I want to make these coefficients 1, because if these coefficients are 1, then I actually reach a point when I can solve it more easily, because I'm just getting x, I don't have to divide by something later. So what I'm trying to do is get to something we call row echelon form, which is getting 1s on those first position points that are actually on the diagonal of the left side of this augmented matrix. So to do that, the first row I would have to multiply by 1/2, and the second row I would have to multiply by that -2 I mentioned. So that gets me 1 3/2 1/2, and 0 1 13. So the second row tells me that y is equal to 13. I don't have to do any additional work to determine that. It's just y is equal to 13 because there's a 1 in the position for y. Now, I still have to back substitute in this way to find x, so I'd have to put the 13 in for y, convert the first row back to an equation, x plus 3/2 times y, which is 13, is equal to 1/2, and then solve for x, which gets me -19. There's an even easier way at the end of the day. We can go all the way to something that we call reduced row echelon form. What this is you continue reducing until all you have are ones on the diagonal, and then everything else is zeros except for that right-hand side of your equations, and the values that are here on the right-hand side will be the values for your x, your y, and your z for the solution. It actually solves it directly. You don't have to divide, you don't have to convert back to equations, you just get your x, your y, and your z on the right. It's awesome. So what you do to get there is you continue the elimination process until you only get diagonal terms, and then you just would multiply the rows by whatever constants you need to make each one of them equal to 1. So rather than doing that earlier, you would do it at the end. So if I continue with an example that we had before, so x plus y plus z equals 4, y plus 4/3 z equals 7, and z equals 3. I already have it in row echelon form. I just want to convert it to reduced row echelon form. So I'm going to work back from the bottom to the top to get rid of these 3 terms that are in that upper triangular part. So the first thing that I'll do is subtract row 3 from row 1, and I'll subtract 4/3 of row 3 from row 2, because row 3 only has the third term, and that one, I need to get rid of 2 of those here. So when I compute the row operations, then I'll have 1 1 0 as 1, 0 1 0 3, and 0 0 1 3. Now I just have to get rid of this 1 that's in the first row. So I take row 1 minus row 2 to get rid of it. So now I have a 0. I have my full diagonal of 1s, and I have a column in the augmented matrix that corresponds to my x, my y, and my z. So x equals 2, y equals 3, and z equals 3. Awesome. Even better news, you can do it on your calculator. So you would just enter the matrix into your calculator and then use the computations in your calculator to determine RREF of A to determine the solution. So I am going to ask you to do some things algebraically, but you'll have your calculator so you can check them. So make sure that you bring your calculator to class so that you can actually try these matrices, because if you don't bring your calculator to class, then you're going to end up missing it entirely this time, and you will want that for your exam. So we will do a few in class, so make sure to bring your calculator so you can actually practice this, because we have done nothing with matrices prior, so this is going to be new. The last thing we need to talk about is still, once again, inconsistent and dependent systems. It looks the same as it did before, but now it's in a matrix form instead of in an equation form. So if you row reduce the matrix down to your what should be ones on the diagonal, but you don't have a 1 in one of those places, and everything else is zeros, and you have constants on your right-hand side that are not equal to 0 for the row of zeros, then you know you have a contradiction, because it's saying that, 6 equals 0, or 2 equals 0, or -1.5 equals 0, which isn't true. And just like before, that means you have no solution to the system. It's inconsistent. However, if that constant is 0, so I have a full row of zeros, 0, 0, 0, 0, in that case we have a dependent system. We have infinite solutions. So more commonly, you're going to get the case that we're trying to get, which is the diagonal of 1s, everything else is 0, and then A, B, and C are X, Y, and Z. That's your one solution case, just like before. But if you run across a full row of zeros, what that tells you is that you have infinite solutions. You have to define a parameter and define your solutions in terms of it. If you have a row of zeros but some constant on the right-hand side of those zeros, well, 0 can't equal some other constant, so you know that you don't have a solution. Just make sure that you bring a calculator so that we can work through examples and application problems in class, because this is not something I can do as easily on this tablet. So, bring your questions, or send me questions. See you in class.